in there with the coefficient of friction and the friction force and whatever, and connecting with societal interests and concerns. So that was one of the ways to connect. So excellent job. All right. So we're just going to continue on in chapter 6. Any questions, concerns? Chapter 6 homework is posted. Somebody can tell me when it's due. I'm sure Amelia can tell me. Monday. Okay, well, that's 6 part 1. So I believe chapter 6 I have divided into 2 parts, and part 1 has to do with work and the work kinetic energy theorem. So that gives you a strong hint as to how you're supposed to do those, and it was sort of the earlier reading that you're doing. So we ended last time. We were doing a worksheet, but it concerned what I call the work kinetic energy theorem. Some books call it the work energy theorem. We'll actually start developing a few different work energy theorems, but the work kinetic energy theorem, how I call it, says if you have something that is behaving as a particle, that means it's a rigid, non-compressible object, or at least it's not compressing at all in between your initial and final state, and it moves rigidly without rotating in between initial and final. So it only translates. Doesn't matter how crazy of a way it translates. It can be doing loops in between, but it can't rotate at all. And it can't be a springy thing that's compressing in between. So we're just talking about a box or something like that that doesn't rotate. Then the net work done on it, that means by all forces. That's what the net work means. Add up all the works done by all the forces, that's equal to the change in kinetic energy, where the kinetic energy is 1/2 mv squared. So that allows you to say, if you know the initial speed and you can calculate how much work was done on it, you could find what the final speed is. Sort of the same way we did with kinematics. It just feels a little bit different here. And you'll find that there are some problems that we could have solved with kinematics to find the V final, or we could use the work kinetic energy theorem to find V final. And here was one we didn't have time to discuss at the end of Wednesday, but let me just read it off. The solution you can see is not complicated. 1500, this is the last one on the worksheet that we were working on Wednesday.
Dr. Kelly, could you share your screen, please?
Oh, thank you very much. I've got it up nicely for the class here, but thank you for reminding me. Okay. So let me read the problem here. 1500 kilogram car moving at 25 meters per second suddenly applies the brakes and comes to stop in a 50-meter distance. Find the work done by the road on the car via friction during this process. So sounds a little bit strange, but we can think of the car is putting a force on the road because the tires are sort of pushing against the road, essentially trying to push the road forward in front of it. And the road is pushing back on the car, pushing against the direction that it's going. So the road is going to be doing negative work on the car in that braking process. And we can calculate from the work kinetic energy theorem the net work done by all forces by the change in kinetic energy. And we've got the initial and final kinetic energy, all the information we need. Initial kinetic energy is 1/2 times 1500, 25 squared, and the final kinetic energy is 0 because it's come to rest. So that's a negative change in kinetic energy. That's not what we were asked for. We were not asked for the net work, but in this case, if you look at the forces that are acting on the car, other than the road pulling back on the car, trying to slow it down, what other forces are acting on the car? Yes, Sarah. There's a normal force and a weight force, and those are both doing 0 work. Hopefully we remember that, right? Because they're perpendicular to the direction of the displacement. So we could say the net work is the work done by the weight force plus the work done by the normal force plus the work done by the road friction force. and only those other two are 0. And so the net work is the work done by the road on the car. And it's a certain amount of negative work because the car is going forward, but the force on it is backwards. That's negative work. Not surprisingly, it's a huge number because the car is going at a significant speed. And more importantly, it's rather massive. Questions on that one? It was just another example using the work kinetic energy theorem that we got to at the end. Okay, we're now going to start to complicate things. Remember we said systems can be complicated. They can be lots of different bits of masses that are connected by forces, kind of like I have these two masses connected by a spring here. A human body is lots of bits of mass connected by lots of different forces, so it would be extremely complicated. But we said, let's start out at the easy end of the spectrum and just look at a particle to begin with. We're now going to start getting into springy kinds of forces. So looking at objects that are not just rigid boxes that don't rotate, but rather they have some squishy internal forces to them, maybe like a rubber ball, or maybe like something connected by springs, or even if you have a mass and you lift it up from Earth. If I consider my object to be this mass plus Earth, it's almost as if there's an invisible spring connecting them, right? The spring wants to contract and pull this to the ground. And when I lift it up, I'm stretching the spring, and the spring doesn't like that, right? It's trying to contract back. So you can think of, if I take my system to be this plus the Earth, it's almost like there's an invisible spring connecting them. That sometimes helps. So along the way, let's just extend work kinetic in kind of a very easy way to systems. And think of so we're going to imagine that there's an initial state where I have maybe 3 or 10 particles, or maybe Avogadro's numbers of particles, but they're all just translating in between the initial and final position. And we're going to imagine that there are some external forces that are acting on all of these particles. But the system is just the individual particles conceived of as a whole. All the forces acting on them, we're just going to imagine come from the outside. Well, of course, because there's multiple individual particles, we could write down the work kinetic energy theorem for each one of those individual particles. And it's sort of tempting to kind of add those 3 equations up and interpret the results. So if I calculate the net work done by all forces on the blue box, and separately on the red box, and separately on the green box, when we say the net work done on this system consisting of these 3 kind of particles, we just mean the sum of those 3 works done by all the forces on all the boxes, all added together. That's what that net work means, okay? Similarly, when I add the change in kinetic energy of the blue box to the green box to the red box, we're going to mean by the change in kinetic energy of the system the total final kinetic energy, all added together, minus the total initial kinetic energies, all added together. That's just what the change in kinetic energy means right here. So in a very trivial sense, we can say it doesn't apply to a single particle, but to collections of particles. And we're going to use that fact a little bit later. Okay, so now let's go on to more complicated kinds of systems for which we're going to find out the work kinetic energy theorem is not true. You can do work on an object and you won't see corresponding changes in kinetic energy, okay? So any kind of system, and I'm going to use, 2 masses connected by a spring to be, an easy example of this kind of system. We're going to imagine, the little bits of masses that form the system are moving to different positions, and maybe these forces are actually, there's a displacement of object 1, displacement of object 2, and the spring might get stretched, even if it's an invisible spring like we were thinking about for Earth, okay? That we're going to think, this is our object. How we were thinking about the box earlier, this is now what we're going to think about doing work on by pulling and pushing on the various parts of the system. We're only going to consider the work done by external forces on this. In other words, as this thing moves, of course, the spring is pulling on the top mass. And that spring is going to do work, right? Because the top mass is moving. And so the spring's pulling on it as it moves. It probably does some positive or negative work. But we're not going to be concerned about that because, we might be thinking about a container of a bunch of molecules. And all little individual molecules, of course, are exerting forces on each other, right? Those little electrons are repelling and keeping molecules away from each other as they bounce into each other under thermal forces. But we don't really know anything about the work done by those forces. Now, what we can control is if we have them in a container and then we compress the sides of the container, so we compress the gas or whatever that's in there, then I might know something about the work that I do on those by virtue of the displacement of the side of the container, but I have almost no control over knowledge of what's going on individually. So this is sort of this is like two molecules and there's a force, but some invisible electronic force between them that we're visualizing as a spring there. So we're going to try to isolate just the work done by forces that we're bringing in from the outside. So maybe there's a force between these two bits of mass, then maybe it's an actual spring, but I might come in with my hands and pull on the sides and I would say, I'm the external force in this case. I'm not going to be concerned about the work done by the spring force. I am the external force, and we're just going to calculate something like that. And of course, there are multiple parts of this. This mass might be moved over to here, and this mass might be displaced over there in between my. We're going to add up the work done on all the bits of the system in the sense that I was just talking about for a system consisting of multiple parts. Okay. Now, the first thing to realize, or the important point, is that if the system isn't rigid like this, if it's got some internal springiness to it, the system need not gain any kinetic energy, even though net work is done on it by external forces pulling on its parts. So the work kinetic energy theorem is definitely not true if you have springy kinds of systems, unlike a particle. Okay. So let's take an example, and I'll actually just sort of do this in front of you. So let me stop sharing and show it on the camera. Here's a spring I found that I attached two masses to. It's the best thing I could find on short notice. Okay, so I'm imagine, forget about gravity. This thing's floating out in space. I'm in deep space. There's no gravity anywhere, right? Completely relaxed, right? This is my system that I'm going to consider. It's not a rigid system. It has some internal springiness to it. I'm going to come in as an astronaut and put my hands on this and take it from this initial configuration, which is at rest. There's no kinetic energy initially. And I'm going to transform it like this. I'm going to stretch it and then bring it to rest in a stretched configuration. Okay, I'm an external force. I'm applying an external force here and over here. And we want to think about the sign of the work in that stretching process. Okay, now when we said a system of particles, we have to calculate the individual works on the individual pieces and then add them together. What do you think about the sign of the work that my right hand did as I stretched? Positive, negative, or zero? It's positive, right? Because I'm pushing with my hand in that direction and it's displaced in that direction. That's the hallmark of positive work. What about my left hand as I stretch like this? Positive also, right? Because both hands are pushing in the direction that the point the force is being applied to is being displaced. So both hands are doing positive work. And that means there's a positive work from external forces on the system. Now, it started out at rest, and I pushed it apart and let it come to rest. So the final state was at rest. And therefore, the change in kinetic energy in this case is zero. The net work done by external forces on this springy system was non-zero, but the change in kinetic energy is zero. So the point is of that is that the work kinetic energy theorem doesn't suffice here. Okay, this is me doing the same thing in the videos. If anybody watched this, just sort of animating it, there I am pulling with my hands. The work done is positive, change in kinetic energy is zero, and therefore this work kinetic energy theorem is not true in this case. We're going to try to define or derive a replacement for it, something that's more general that will work with these kinds of systems. Similarly, this is an exaggerated system or a picture, but it's supposed to be a book here near the surface of Earth, but I drew the book really large and really high up just because that's the only way I could draw it. And I'm going to take my system to be the book plus the Earth, where gravity I'm going to think of as an internal springy force that always likes to contract things down. It's like an invisible spring that I can't see. Okay. And as I use my hand as an external force, okay, so I imagine here I am coming in as an astronaut. I place my hand underneath and I pull it up and raise it to a higher height above the Earth. It's not supposed to be in outer space here. We're imagining we raise it up 10 meters near the surface of Earth, but that's just how I drew it. Then if I calculate the amount of work done by my hand, again, it's positive here, right? I reach in with my hand, that's an external force, and it's doing positive work because it's pushing up and it's being displaced up. And yet, if I raise it from rest and then come to rest at the end of it, there's no change in kinetic energy. It's almost the same kind of system. Okay, so with these more complicated systems, you can kind of see that it really matters that I define carefully, especially in this Earth example, what my system is. In other words, I might have just considered the book by itself to be my system, and then I would have said the book's behaving like a particle. Look, it's just translated up. But if I say my system is the book plus the Earth with that internal invisible springy force between the two, then it's not behaving like a particle, and I don't expect the work kinetic energy theorem to apply. So just to show that other case, if I take, we're going to have to be very careful to define exactly in each problem what our system is. If the system is just the book, hey, then it's a particle. If I look at what forces now are external forces, well, the gravity is not an internal force between two parts of the system anymore. I have to consider the weight of the book to be an external force. And now there are two external forces acting. And as I raise the book up with my hand, the whole time gravity is pulling down. And we can imagine that if I it's maybe not completely clear that this is going to work out this way, but if I raise it from rest up to rest, just like I did before, change in kinetic energy, of course, is zero, but I'm doing positive work, gravity's doing negative work, and they exactly cancel, so it would be zero. So this would be a case where we could use the work kinetic energy theorem. But we're not always going to want to look at things like this, so we want to find a replacement for the work kinetic energy theorem in more complicated cases. Okay, so just to summarize what we have so far, we've got our work kinetic energy theorem that only applies to a rigid non-rotating object. And now we're going to consider a non-rigid springy system consisting of masses interacting via some what we'll call internal forces. We mean forces between the parts of the system. And we're only going to concern ourselves with work done, the net work done by external forces, not the internal forces. We have to be very careful to say what's internal and what's external. And we want to figure out what belongs on the other side of this equation. So let's go back to that system where I was just demonstrating pulling the two masses apart with the spring connecting them. And I'm going to think of this as my system and the spring as an internal force. And so the only external forces that were being applied were the forces from my hands as it was stretched out. We're actually, in order to be able to derive what the change that's needed is, we're going to think of this a different way. Another way to think of this process is to think of these two masses here as independent particles, just like I started this lecture talking about. We can think of them as independent particles. And then there are four forces at play. My two hand forces, but there's also a separate spring force pulling back on each one of the sides. And we're going to consider all of those just for a second to be external in order to figure out what's going on. And then we're going to go back and reinterpret them as internal forces, because all we've really got is the work kinetic energy theorem. So forgetting about the spring as an internal part of the system, if I now just think of my system as looking like this, there are these four forces that are acting. In that case, I can apply the work kinetic energy theorem as long as I include all the forces that are acting on those two sides. But because I know I want to separate out the external forces, that just includes my hand forces, from the internal forces, that's going to include the spring forces on the two sides, I'm going to explicitly separate them out now. And I really just wanted this work done by the external forces on the left-hand side. So I'm going to subtract the internal force networks done on the pieces of the system off on the right-hand side. And then we're just going to redefine something here. And this will require a little bit of explanation later. I'm glossing over something that we'll get back to and elaborate on more. We're going to say the negative of the net work done by all internal forces, in this case, it's just the spring forces on the two sides that are moving. We're going to redefine that to be the change in something called the potential energy. So you can just think of it as a renaming process here, or rebranding. And therefore, our new version of a different form of work energy theorem that applies to springy systems as well is that the net work done by external forces on some kind of springy system is equal to the change in kinetic energy plus the change in potential energy. Now there's a problem here, and that's that we don't know what the potential energy is yet, so we're going to have to work a little bit to figure out what potential energy function, or how to calculate that change in potential energy. So that's the next part of this. And I apologize, there's quite a bit of explanation here, probably without a worksheet maybe today, just to kind of explain where all this stuff comes from. Okay, so we just found out, here's our next version of a work energy theorem. It's not the work kinetic energy theorem, but it applies to springy forces. And now the question is, how do we calculate the change in potential energy for an internal spring like that one I was talking about, or for an internal gravitational force, which is kind of like an invisible spring that always wants to contract? Okay. So let's do it for a gravitational force. And I'm going to imagine, again, it looks like this book is really outside the atmosphere of the Earth, but we're imagining it's right next to the surface of the Earth. I just wanted to be able to draw an ellipse around that whole thing. So we're going to use the form mg for the weight of the book. I'm imagining that book is really close to the surface of the Earth. Okay, so just like we did before, I raise my hand. My hand is the only external force in this case, but let's draw in the internal force that's acting on the book as it's raised. And remember, I'm thinking of this whole thing, Earth plus book as my system. So the book is being displaced. I might have to think about the work done on Earth too. The good thing is I don't have to really think about it because Earth's not essentially, like when I take a book and raise it up, the book does all the moving. Earth essentially stays still, and that's just because it's so massive. And in order for work to be done on something by an internal force or an external force, the thing has to move. There's no work if the point where you're applying the force doesn't move. So I don't really have to think about the Earth because it's not moving. I can just think about the movement of the book here. But it's important that my system includes both of them. Now, so we're going to go back to our definition. The change in potential energy is equal to the negative of the net work done by internal forces. And in order to do that, let's just put a little coordinate system here. I'm going to take the plus y-axis to be in the direction up from Earth, wherever you're doing this experiment. Okay? And imagine that the book goes from some initial y-coordinate, y initial, to some final y-coordinate, y final. And let's go back to our definition, my rebranding that I just did a second ago. I said the change in potential energy is just a different name for the negative of the net work done by internal forces. So there's only one internal force I have to think about here. That's the one shown in red, the weight of the book. And so this is the negative of the work done by the gravitational force on the book. I'm carrying this minus sign carefully through in every step, right? There's a minus sign in front of that work. There it is appearing right there. Now, the work itself done by gravity, is everybody okay with the fact that that is negative? That's why you're seeing a double negative there, right? I had a minus sign in front of it, but the work itself is negative because gravity's pulling down as I'm raising it up. And we know how to calculate that work, right? The gravitational force is constant, so I can go back to my old Fx delta x formula for a constant force doing work. It's negative. the magnitude of the force is mg, and the distance it got displaced through is y final minus y initial. So just let's cancel that double negative and just distribute everything out. That says the change in potential energy is equal to mg y final minus mg y initial. Now, I'm calling this a change in potential energy, and notice I have something final minus something initial. That seems like we should define the gravitational potential energy for a system consisting of a mass and Earth, where that internal gravitational force is what we're going to consider to be internal. The gravitational potential energy is the mass times little g times its y coordinate. And we'll find out. It doesn't matter where you measure y from. You can measure y from the floor, you can measure y from anywhere. But the important thing is that plus y has to be up. We derived this formula by assuming that plus y was up from Earth. So you always, when you're going to use this potential energy formula, you have to take plus y going upward from Earth. Okay, so one way to think about this is the gravitational potential energy of the system consisting of my book plus Earth increases as I raise the book further away from Earth. I'm increasing the potential energy kind of stored in the system. We'll develop that in just a second. Okay, so there's our first potential energy formula that we've got. The potential energy, the gravitational potential energy stored in a system where gravity is an important internal force, and you have to be using it where your mass that you're moving around is near the surface of Earth, because I assume the weight was m times little g, is mgy, where plus y is up. Okay, so I already pointed out that the potential energy increases as you raise the object farther from Earth. We're going to get that intuition more as we go on. Why do we call it potential energy? Well, we call it potential energy because, well, when I put potential energy into the system, so my system again is Earth plus mass, and I put some more potential energy into the system by raising this mass up further from Earth. We call it potential energy because it's potential because it can be turned back into kinetic by letting things go like that. So it's like energy that's stored in the system, but you can get some, more visceral energy, kinetic energy out of it. Kinetic energy is energy of motion, 1/2 mv squared. So when something's going faster, we've converted that potential energy into kinetic energy. Okay. Can't remember if there's one more comment here. No. Okay, so there are potential energies that might be associated with lots of forces. So this is the potential energy that you're going to use when you have a system consisting of Earth and some mass, and the internal force is the invisible springy force between the two, right? It always wants to contract downward. Yeah. No, it doesn't matter if y goes negative. In other words, let me just draw something on the board here. Okay. I might have Earth down here. We're really close to the surface of Earth. And for some reason, I choose y equals 0 there and plus y is there, right? So I bring my, I bring my book from y equals -5 up to y equals 2. I would then say, still, the change in gravitational potential energy is going to be mg times y final minus mg times y initial. And notice the minus times minus gives me plus, so that's going to be mg times maybe 9 meters there. So you just keep the minus signs. You don't ever flip anything. I'm just using this formula, mgy final minus mgy initial. And if y initial happens to be negative because I chose 0 to be way up here, that's fine. Just keep those minus signs rolling along with it. Is that enough on that? Okay, so we're gonna, you might think, well, gosh, there's a lot of forces we've discussed so far. Do we need a different potential energy formula for each one of them? And the answer is, well, potentially we could have a lot of these, but we're going to limit how many we deal with in this class. The only other two cases in Physics 110 that we're going to discuss is if we have two masses that are connected by an actual spring, we're going to get a potential energy formula for the spring. In other words, you might think if I have these two masses here that are connected by a spring, I can store potential energy in the system, right? By stretching it apart like that, right? Because I could get a lot of kinetic energy by letting it go and they would zing together, right? If this were the kind of spring that I could actually compress, it doesn't compress very easily, but imagine it's relaxed like this and I push it together like that, then there's potential energy stored in it again because it wants to go apart and I could get kinetic energy out of it. So that's why we call it potential energy. So we're right now going to get an expression associated with the spring, potential energy stored in there. And then finally, we're going to get another gravitational potential energy formula that's the one we've got right now is only valid when one of your objects is near the surface of Earth. We're going to use our gm1m2 over r squared gravitational formula from Newton to derive, or actually just write down, a potential energy formula that's valid when you drop something maybe that's 2 moon radii above the surface of Moon and then drops all the way to the surface of the Moon and would allow us to calculate the final speed at the bottom. We're not going to derive that one because you have to use some calculus to derive it, but we'll just say what it is. Okay. So we're going to, in order to talk about, again, I apologize for talking so much in a row, but I just don't have to, in order to use these, we've got to develop the potential energy formulae associated with them. Yes?
So the equation has the delta potential energy equals.
Yeah, so the only one we have so far is, you can either think of it like this. Gravitational potential energy, it can only be used when your object is near Earth and your system is an object plus Earth, where gravity is an internal force, is mgy final minus mgy initial, where y is upwards away from Earth. We haven't learned about spring forces. We'll talk about friction later, and there is no gravitation, there is no potential energy formula for friction. We haven't talked about normal forces. We still got to think about a lot of things, right? But we're going to concentrate on the ones we're going to use first. Okay, so in order to get one for springs, or at least understand how to use it for springs, we've got to talk a little bit about spring force. So if you have the right kind of spring, it has a certain relaxed position where it's neither compressed nor it's stretched out, right? So if you just let a spring go to its equilibrium position, that's where it's not exerting any force on the end. So here's a spring. I'm imagining it's the same spring, but I'm just drawing it in 3 different positions. And we've attached one end to a rigid wall, and the other end is attached to a mass that we might, be concerned with, but let's not worry about it too much. And we just decide we're going to measure a position somewhere on the mass. On this mass, I've decided I'm going to measure the position of the left end of the mass. And we're just going to, draw that on an x-axis here, where the stretching direction is the positive x direction. Doesn't matter where you choose on the mass. We just need some point so that we can know how far it's been stretched. We're going to let the spring be completely relaxed. And at that point, whatever point you chose to mark on your mass, for me, it was the left edge, we're going to label that x equals 0 on the x-axis. So always x equals 0 means the spring is neither pushing nor pulling. It's completely without tension or compression. If you stretch your spring, we're going to call that a positive x down here. And if you compress the spring, we'll call that a negative x there, okay? When I stretch the spring, of course, the spring force pulls back against the direction that I've moved it, right? If I stretch the spring out, beyond its equilibrium position, isn't the spring force on that mass pulling back to the left? It doesn't want to be stretched, so it's pulling back against that direction. Hooke's law tells us exactly, as a function of x, depending on how far you stretch it, how strong the spring force is. And it gives the x component of the spring force, and the minus sign is telling us that when you stretch this to a positive x, the spring force has a negative x component. That's what the minus sign is about, right? And as long as you don't stretch it too far, it's proportional to x, and the constant of proportionality depends on the spring. Usually we call that the spring stiffness. If you have a really thick spring, it's really hard to compress it and it's hard to stretch it. If you have a slinky or something like that, it's pretty easy to stretch it. So one that's hard to compress and stretch, that would be a large K value, and that K is called the spring constant. And one that's easy to stretch, that would be a small K value, okay? So K is called the spring constant. You can see by solving up here that its SI units are going to be newtons per meter, just by solving for K up there. And small k is a weak spring, large K is a stiff spring. This also, the minus sign there also tells us about compressions. Notice if I compress to a negative x value, the spring force x component is in the positive x direction. And it looks like it's always in the negative x direction, but if I've compressed it, x itself is negative. So I have a minus negative, and it's actually going to give a positive component, okay? Here's the part we're not going to derive. And you actually could use some geometry without calculus to derive this, but the associated potential energy, if we thought about calculating the work that's done as you move this from one position to another, we could calculate the potential energy stored in the spring is 1/2 times the spring constant times the x that you've stretched it to or compressed it to squared. Okay, what does that mean? That means that if the spring is relaxed, we're going to say there's no potential energy stored in it. I can't get anything out of it. If I stretch it out at a stretched position, then x is going to be positive, right? I just say, how much longer is it than it is in its equilibrium position? And that would be my x, right? Because this is x equals 0, wherever I'm measuring from here. I've stretched it a certain amount. And notice that it doesn't matter whether I stretch it or compress it. If I stretch it by 1 meter, x would be 1. If I compress it by 1 meter, x would be -1, but it's being squared, so the minus sign goes away. I'm storing the same amount of potential energy in it, whether I compress it or stretch it, if it's the kind of spring that you can compress, okay? So that gives us our second potential energy formula. It's potential energy stored in a spring, and you got to know, again, just like we had to know plus y was up here, I have to know what x equals 0 means here. X equals 0 means the position you're measuring, that's where it's at when the spring is relaxed. The third case, and again, this is just going to come out of nowhere because you really need some calculus to derive this one, is that if we have two spherical masses, or a spherical mass and something small, so just to draw this on the board, suppose here is Earth, and up here is the moon, or something like that, right? And just like before, we're going to define r to be the distance between the centers of the spheres in whatever configuration they're in. The potential energy stored in that configuration, right? There is some potential energy, because if I just held it at rest and let it go, these two are going to come together. I'll get some kinetic energy out of it. So clearly there's potential energy stored in it. The potential energy has the formula that's almost similar, but sort of annoyingly different than the one we already know. Minus capital G, that's 6.67 times 10 to the minus 11, times the mass of Earth times the mass of the other one, the product of the two masses, whatever they are, divided by r, not r squared. Comes from some calculus. You may, if you've taken integration calculus before, you may know that if you integrate 1 over r squared, you get a -1 over r, and that's where it comes from. So it's not too hard of a derivation, but we're not going to talk about calculus in here. Okay, so that's where that formula shown down there in green at the bottom is coming from. This is how much potential energy is stored. Now, this one really looks strange because it's got a minus sign in front of it. And you might think, well, isn't it getting more negative if I pull the moon away from Earth? Is it becoming more negative because the minus sign is there? And the answer is no. You really have to think about how to think about this. So here's an object. And what I'm plotting is the gravitational potential. So here's an object of mass m, somewhere at a certain distance r from Earth. And I'm plotting minus g times the mass of the object times the mass of Earth divided by r as a function of r. So we bring it from really close to Earth to really far away from Earth. And notice that everywhere it's negative here, it's always below the r axis. That means it's a negative value of the function. But the important thing is not that sign, but rather the fact that if I take that object and bring it further from Earth, isn't it still true that the potential energy is increasing, right? Just like it's true near Earth, that if I take an object and lift it up, we already observed the potential energy is increasing. I'm putting more potential energy into the system consisting of this and Earth with the invisible spring there. Same should be true for the moon and Earth if I move the moon farther away. Or if I have this, 1 Earth diameter above the surface of Earth, then I move it a little bit higher. So I can't use the simplified formula for the gravitational potential. We're still putting more energy into the system, and that's what really matters. So we do really have to be careful in keeping this minus sign around when we're doing calculations. It's an important minus sign, and we'll see that happening soon. Okay. So we've got our full list of potential energy functions there that we're going to do. And now what I want to do is, if we have time, we've got about 9 minutes left in the class today, at least start on an example. Okay. Now, I think, I can't remember exactly how much reading I had you do, some of the work on potential energy in the reading that you were doing. Sometimes people define the sum of the kinetic energy plus the potential energy in a system, right? A system you might say, my system is this marker plus Earth with the internal gravitational force between them. And as I drop it, when it's halfway to the floor, the system has some kinetic energy. Now the Earth's not moving much, so its kinetic energy is essentially zero, but the pen had some kinetic energy. Plus, it still had more contraction to do. That spring wanted to contract even more, so there was some potential energy in it. And sometimes people define the sum of kinetic plus potential to be mechanical energy. I think Giancoli does that in the book, so you might see that, and we'll use that terminology a little bit later on. Now, we just said in this formula, our new version of the work energy theorem, that the net work done by only external forces is the change in kinetic energy plus potential energy of the system. We're going to find a lot of cases where if we define our system right, sometimes we just throw everything into the system. So there's no external forces left to pull on parts of the system. We'll make everything internal in the system. In that case, it might be true that the external forces do zero work. And so the kinetic energy plus the potential energy change in that is equal to zero. And sometimes call that conservation of mechanical energy. That's one of the cases, if I say, hey, there's nothing in the world or nothing important other than this pen and Earth, and I'm going to let it go. It started out that it had a lot of potential energy, but no kinetic energy. As it falls, the potential energy decreases, but the kinetic energy increases as it goes down. What this is saying is that the change adds to zero. However much your potential energy goes down, your kinetic energy goes up by the same amount. That's only because there weren't any other external forces doing work. If I, as an external force, reach in with my hand and slow it down, it might lose a lot of potential energy, but not gain that much kinetic energy. And so that wouldn't be true anymore. But if there are no other external forces to do work, we say mechanical energy is conserved. Conserved just means doesn't change from initial to final. and potential energy is going down and kinetic energy is going up. Opposite would be true if I threw this up, right? Then potential energy would be increasing while kinetic energy is decreasing as it slows and rises. My hand's not there. Okay, let's do an example. I don't know that we're going to have a chance to do the worksheet that I brought today, but we'll at least look at an example here. So a ball is tossed straight up. I'm going to choose, I could take my system to be just the ball, and then it would be a particle, and I could use the work kinetic energy theorem. But instead, because we've got some more tools at our disposal, let's take the system to be ball plus earth, where gravity is going to be an internal force. Okay, I'm going to be very careful to define my system. And, air resistance might have been a force, but let's assume that it's negligible in this problem. In this case, since air resistance is negligible, and the only force of significance that's pulling on the two parts of the system is the internal force, that means external forces aren't doing any work. And that's a case where mechanical energy is conserved. And in this case, as the ball rises, potential energy is going to increase and kinetic energy is decreasing. And the same opposite happens as it falls. We already kind of talked about that. What about if air resistance were not negligible? Let's think about that case carefully. If I throw it up and the ball is on its way up from an initial to a higher final state, and I say, gravity in between this ball and Earth, that's going to be an internal force, but that air resistance force is going to be an external force. Is the work done by that external force positive, negative, or zero as my system goes from, the one thing rises away from the Earth? It's going to be negative, right? Because air resistance always tries to slow things down. So it's pushing in the opposite direction it's moving. So while the ball is going up, air resistance is pushing, or air drag is pushing in the opposite direction. Okay, so in that case, the net work done by external forces would be negative. And that means compared to how much potential energy that it gains, it doesn't, am I going to say this the right way? Probably better write it down to make sure I don't make a mistake. If we write the net work done by external forces, I always write it as W net by X equals the change in kinetic energy plus the change in potential energy. And we say, in this case, our external force was air resistance, so it's doing some negative work. That means that, for example, the change in kinetic energy is going to be equal to minus the change in potential energy plus something a little bit more negative. So I got a negative thing here, and I'm adding a little bit more of a negative number onto it. So it's going to slow down even more than you would have thought. And that makes sense, right? If I put air resistance in there, for a certain change in height, it's going to slow down even more by the time it gets to that height, because the air resistance is helping slow it down just like the gravity was. Okay, here's a second example. We got 2 minutes left. Let's see if we can explain this. Small mass connected to a large asteroid by a spring. So the asteroid's supposed to be so big that it's not going to move as the thing oscillates. So I've glued one end to the asteroid, and then there's a small mass that's connected to it. And if I stretch it and let it go, it might oscillate back and forth, as the spring compresses and stretches. My system I'm going to choose is going to be the mass plus the asteroid, and the spring is going to be an internal force, just so I could use my new formula there. Of course, there's always a gravitational attraction between any bits of mass, but we're going to assume we can ignore that because they're not Earth-sized kinds of things. It's going to be a small force. Okay, asteroid doesn't move. In this case, the spring force is the only relevant force. If I can ignore that gravitational force, there's no air resistance, and therefore the net work done by external forces, there just aren't any significant external forces. That's zero. And so again, mechanical energy is conserved. Our spring force is 1/2 kx squared. Spring potential energy is 1/2 kx squared. And that means as the spring potential energy increases, so here's the asteroid. My left hand over here is the asteroid. As this is going out, as the spring potential energy increases, the speed of the system, kinetic energy, decreases. As the potential energy decreases, the speed increases. Then it passes equilibrium. Now, as it starts compressing, potential energy is increasing, which means the speed is decreasing. So always those two are sort of connected that way. So we're going to use conservation of mechanical energy a whole lot. And I'm just clicking on this to see. Yes, exactly. Okay, so that's good. We're up to the worksheet, and we will do the worksheet on Monday. Again, the homework that I have due Monday, and I'm happy to answer questions after, even right now for a few minutes, or after class on Monday, or during office hours on Monday if you've got questions on that homework. But that's only having to do with the earlier stuff on work and work kinetic energy theorem. I'm going to, this weekend, put up the second half of this that will be due late next week, probably. Have a wonderful weekend.